Now, there are a lot of integration rules that come along with this notion of a definite integral. And you can see that I have 6 of them posted right here. The purpose of this video is not to present you with them and then make sure you know them by heart, but rather to explain that each and every one of them makes sense if you have in your mind the right understanding of what a definite integral means. And that meaning that we associate to a definite integral is the meaning of area. Now, we're not going to go through all 6 of these integration rules, but we're rather going to go through 3 of them, trying to make sense using pictures and the definition of a definite integral. So let's start with this first rule, that the integral from a to b of the constant function c is equal to c times the quantity b minus a. That might just seem like a nonsense rule without the right picture. In order to visualize this, let's take a look at what we are being asked to find when we're asked to evaluate the definite integral that you see right here. What we're being asked to find is the area between the curve f of x is equal to the constant function c, which we've drawn right here, and the positive x-axis on the interval from a to b. Looking at this picture, it's clear to us that that area is the area of a rectangle, and the area formula for the rectangle is the width times the height. For this function, our height is given by that constant function c, and our width is given by the difference in the x values that define the interval. In other words, b minus a. So altogether, the area of the rectangle we have drawn here is the width, b minus a, multiplied by the height, which is c. And that is why we have this equation. Both of these things, the integral from a to b of the constant function c multiplied by dx, and this expression over here, c times the quantity b minus a, both of these things are representing the area that we have drawn here, and so these two values must be equal. Let's pick another example of property number 5. Now, property number 5 is written here with plus or minus signs here and here, indicating that the equation is true with either a plus sign in the place right here, and likewise a plus sign over here, or with minus signs here and here. We're going to draw a picture just demonstrating why this equality holds with the plus signs. Now, this expression that we're looking at is really talking about 3 different areas. Now, the first area we have to consider from this expression is the integral from a to b of this function f of x plus g of x with width dx. The function f of x plus g of x is obtained by taking the values of the function f of x and the values of the function g of x and adding them together. In terms of this picture, f of x has a particular height, g of x has a particular height, and we want to be looking at new rectangles that have height f plus g of x. So these rectangles that we would draw in this image would have a blue bottom part and an orange part on top of that. That's the area being described on the right-hand side. All that's happening on the left-hand side is we're separating the blue and the orange areas. Instead of individually looking at blue plus orange, and blue plus orange, and so on, all the way from A to B with our rectangles, what we're doing is saying, first, let's compute the blue area, just the area shown to us with the function f of x on this interval from a to b. Then, let's compute just the orange area, shifted downward, not stacked on top of the blue area. All this equation is telling us is that I can first find the blue area and the orange area separately if I'd like, and add them together. Or I can add them together first and then do a single computation of area. Either way, I'm going to get the same answer. And that's all that's really being expressed with this sum rule, rule number 5, right here. Now the very last thing I'd like to go over is this example 6 right here, which talks about if I have an integral from a to b of the function f of x dx, that should be equal in value to the exact same integrand, but with the limits of integration switched, if I add a minus sign. Now I don't have a picture for what's going on there, but I do have an explanation that comes from the definition of our definite integral. So let's remind ourselves what that is. Our definite integral with lower bound a and upper bound b comes from this more cumbersome computation on the right-hand side. And what the a and the b were used for was in determining the width of the rectangles we were considering. And when we wrote down this width, b minus a over n, we thought of that as a positive thing, with b being a larger number than a, so that this quantity was truly representing width. All that would happen if we were to switch the a and the b values over here on the left so that b is on the bottom and a is on the top, is we would switch the places of a and b right here. And instead of a b minus a in this numerator, we would have an a minus a b. Now b minus a and a minus b are not exactly equal to one another. What a minus b is in terms of b minus a is the negative of b minus a. And so that's where that additional minus sign is coming from. It's something of an orientation on the a and the b. If we switch them around and put them the other way, this is just another example of how we're computing signed area instead of actual area. So that's an explanation of this last integration rule of the 6 that we've considered here. Now we're not covering the other 3 in this video, but pictures can be drawn for each and every one of them that can help make sense of those rules in terms of area. Once you've got these rules understood, or you know where you should go to look them up, you can put them to use practicing problems like this, where you're given nothing specific about 2 functions, say f and g, other than the value of their definite integrals over different intervals. You can then deduce the values of all sorts of other definite integrals just based on those numerical values by applying your rules of integration. If you're part of my class, you'll be doing some of these computations as part of your work for watching these videos. If you're not part of my class, I encourage you to try them. They're not too terribly difficult, and I think you can do it.